So, thank you for being patient with me, and thank you for watching this video. We're going to finish our last lesson for the quiz on Wednesday. You'll have some practice today. You'll have a review sheet tomorrow, and those answers will be online. And if there's any serious last-minute questions, I can maybe answer them on Wednesday. So yeah, I think this one's going to be less than 15 minutes, hopefully, if I can just shut up and start the lesson. So yeah, let's do it. Friday we talked about chromatic coloring. That's awesome. So know that stuff, know how to do those applications. We also talked about trees, and we're about to talk about the application with trees. So let's just recap real quick what a tree is. It's a graph that's connected. It has no cycles or circuits. And yeah, that's about it. Okay, today we're going to be trying to find the minimum spanning tree. Remember that a spanning tree is a subgraph of a network that includes all vertices and contains no circuits. So this is a tree. This is not a tree because of the circuit. This is not a tree because it's disconnected. And this is a tree because there are no circuits. Okay? Everything branches off from the point. Okay? Feel good about trees? We're good? Great. So here's another, remember we talked about this example on Friday. This is just an example of a tree. Okay, that's not how you spell internet. But that is, so remember this is the example of the internet I was talking about. Okay, look how like this part right here is being branched off from, and there's a lot of activity going on here. This is showing all the connectivity. That's kind of what a tree does. It shows things that are branching off. It shows all the one-way connections to other places, other portals. Okay, so just a good example to kind of refer back to. All right, so with trees, our application that goes with them is to find a minimum subgraph, a minimum spanning tree. Okay. There are certain requirements that go along with this. Okay. The network or the graph we're looking at, it must be a subgraph. Okay. All edges must come from the original graph. We do not need to use all of the edges though. Okay. We're trying to find a spanning subgraph. It must include all vertices from the original graph. And the network must be a minimal, okay? The total weight should be as small as possible. There's no need for any circuits. So basically what all that's saying is I'm trying to find a minimum spanning tree. I'm trying to find a subgraph of a tree that covers, or of a graph that covers every single edge that has no circuits. So here's an example of a spanning tree. Starting at D, going to B, A, C, down to G, F, E. That red graph I drew, that is a spanning tree. That is a subgraph that touches every vertex that is a tree that has no circuits. The goal of our lesson is to identify the minimum spanning tree, the smallest tree. All right, there's a lot of application, a lot of usefulness for this. Okay. A tree shows the connection to all other vertices, the shortest path, the smallest weight that everything is connected. This could talk about price, this can talk about time being saved, this can talk about a lot of things. We need to know how to find the minimum way of connecting all these points, the minimum spanning tree. All right, so in this next example right here, okay, a minimum spanning tree would be probably X here, 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 here. That is an example of a tree subgraph. This was a circuit. This edge right here was unnecessary. That's not going to be part of our subgraph. Okay, we don't want to have a circuit. Edge XY is unnecessary here. The graph doesn't need XY to be connected. A minimum network should have no circuits. All right, edge XY is called it's just called a useless connection. Okay, we don't need it. So the question is, how do we figure out that minimum spanning tree? How do we find a tree subgraph where all the vertices are connected, no circuits, and has the smallest weight? There's two methods, and I'll expect you to know how to do both methods. Okay, it's kind of like brute force and nearest neighbor. The first method is Kruskal's method. All right, Kruskal's minimum spanning tree algorithm. Let's read through the steps together. First step is examine the graph. If it is not connected, there will be no minimum spanning tree. Okay, most of the time, it will always be connected. Step 2 is to list the edges. List the edges in order from shortest to longest. Okay, you want to put your edges in order from the shortest weight to the longest weight. Ties are broken arbitrarily, meaning if they're the same weight, just pick one to go first. All right, once we have our list, then we're going to go through and we're going to darken the first edge on the list. The first edge on the list, the one with the smallest weight. We're going to select the next edge on the list. If it does not form a cycle with the other darkened edges, we're going to darken it. Okay, and we're going to continue doing that until we have, and we're going to keep doing step 4 until we have n-1 edges of the graph have been darkened. If there is, say, 5 vertices, we're going to have 4 edges darkened. If we have 10 vertices, we're going to have 9 edges darkened. The vertices and the darkened edges are a minimum spanning tree for the graph. So, let's go ahead and do this example together. All right, it's step 1's complete. We're good there. Step 2, let's go ahead and list it in order from smallest to biggest. So I think the first one is going to be, let's see here, AB with weight 4. All right, then we're going to have, looks like AE. So I'm just going to kind of, AE with 5. Okay, so we did this one, we did this one. The next lowest one will be BE with 6. All right, after that, it looks like we have CE with 7. All right, after CE, it looks like we have ED and DC with 8. It doesn't matter which one you put first, just put both. So I'll put ED first, why not? And then DC with 8 as well. Then we got BD and CD both with 9. Oops, not CD. DB and BC, my bad. And then our last edge is AC with weight 10. All right. So step 2 has been completed. We listed all the edges from lowest to highest. Okay? Now I only darken those lines just so I can kind of keep up with the edges I used, okay? So, next, step 3 says darken the first edge on the list. So AB, I'm going to go ahead and darken with 4. Okay? So, that one's done. Next, it says move to AE. Darken that if it doesn't make a circuit, which it doesn't. So I'm going to go ahead and darken that. Okay? Then it says to do BE. Well, if you notice, if I do BE, that's going to make a circuit. That's going to make a triangle. And I don't want to do that. Okay? I don't want to make a triangle. So I'm going to skip BE and move to the next one. CE is next on the list. So let's do C to E. That does not make a circuit, so we're good. And then ED with 8. So if I do E to D, that works. There is no circuit. Okay? So if you notice, this graph had 5 vertices, and we just went through 4 of the edges. And if you notice, we have a subgraph. All right, we have a subgraph that connects all the edges together, and we're good. It connects all the vertices together, A, B, C, D, and E. There's no circuits. This is a minimum spanning tree. Okay? So you don't have to redraw it. I'm cool with you just leaving it like that on the quiz, but this is our minimum spanning tree subgraph. Okay? This had a weight of 4, a weight of 5, 7, and 8. All right, so not bad. The weight of my subgraph is just 4 plus 5 plus 7 plus 8, which is 24. God, I hope I did that right. 4 and 5 is 9, 16, 16, 8, 24. Good. So that's Kruskal's method. It's a little bit long. Okay, all you gotta do is just be able to list all the edges in order, and then darken the edges based off of it. Make sense? Oh, 10 minutes. I gotta go. Oh, don't worry. I'm gonna keep it under 15. I'm feeling it. Okay, so the next one is Prim's minimum spanning tree algorithm. So this is Prim's. We just did Kruskal's. Prim's is a little bit faster. I like Prim's. You don't have to list all the edges like you did with Kruskal's. Step 1 says to find the shortest edge on the graph. Darken it and circle its 2 vertices. Ties are broken arbitrarily again. Then you're going to find the shortest remaining undarkened edge having 1 circled vertex and 1 uncircled vertex. Darken this edge and circle its uncircled vertex. And they're going to repeat this until all of them are circled. Okay, until all vertices are circled. I mean, don't let the circle and the underlining and darkening, don't let that confuse you. Okay, so let's just go through the first example together. All right, so the cheapest edge on there is either AC or BC with both weight 3. Doesn't matter, just pick one. Let's do AC. So I'm going to darken its edge. I'm going to circle its vertices. So there's one edge of my subgraph. Step 2 says find the shortest remaining undarkened edge having 1 circled vertex and 1 uncircled. So basically it just wants me to branch off of this edge to the next smallest weight, which is BC. Okay. Then it wants me to find the cheapest one from there that connects to the last uncircled vertex, D. In this case, we're probably going to go with AD. That's the next cheapest one of 4 that connects all my vertices. There's your minimum spanning tree. I connected all the vertices with the lowest weight. There we go. Okay, so if you want to add up the weights, that's 3 plus 3 plus 4, which is 10. Okay, so that's the weight of that minimum spanning tree. If you want to draw it, make yourself happy. I don't know. Boom, 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 boom. B, C, A, D. Okay? That's the minimum spanning tree. Oh, baby, I got 2 more minutes before I'm at 15. Okay. It's just because I won't shut up. All right. Let's try this next example. So the method says find the cheapest weighted edge, and that is AF with 3. So I'm going to darken it and circle its vertices. Now, we got to branch off of that. We got to find the next cheapest one that branches off of that. And it looks like that's going to be either AE or BF. It doesn't matter, just pick one because they're both connected to AF. So let's go here. Okay. See, it doesn't matter because the next step is to pick the next cheapest one, and it's the other one with a weight of 5. So we're going to use that one and go there. All right, so then we got to find the next cheapest weight that branches off of that. And I believe it's going to be FD with a weight of 9. Okay. I have not made any circuits. Nothing's unbroken. We're good to go. And then lastly, the cheapest weight to connect to that last vertex C looks like it's going to be BC with a weight of 13. So there's my minimum spanning tree. That darkened little subgraph there. If I ask for the weight, just know to add them up. 3 plus 5 plus 5 plus 9 plus 13, which is 19, 22, 35? Sure, we'll go with 35. Hey, look, I finished it under 15 minutes, but I'm going to keep rambling on past 15. Just know that this is all you need to know for the quiz up to this point. You're reviewing with some practice sheets today, a review sheet tomorrow. I'll have the answer keys up. Yay, everything's good. Oh, and notice in this example too that we have 1, 2, 3, 4, 5, 6 vertices, and the number of edges we used was 1, 2, 3, 4, 5. So it's always one less than the number of vertices we have. Okay, I'll shut up. Y'all have been awesome. We'll go over any questions you may have early Wednesday, but I'm still planning on quizzing Wednesday. Okay, I'll shut up. Okay, bye. Okay, bye. Okay, bye.